Okay, so beginning Unit 8. Unit 8 is all about polynomials. And we're going to learn how to add, subtract, multiply, and even divide them. And that'll be a lesson in and of itself. How to factor them, how to graph them to some degree. Some graphing them is kind of complex, kind of needs calculus. All right, we got one lesson. We're going to turn back on the switch, as I say. Right now, switch is off for complex numbers. We spent all of Unit 7 using imaginary numbers. We're switching that back off. In the last lesson in this unit, for a little bit of time, I want to switch it back on if we can. But for the most part, off. So, square root of a negative number, don't do it. Got it? All right. Okay. Each of these expressions here are polynomials. However, these are not polynomials. So I feel like sometimes it's easier to understand something if you see what it isn't, right? So it is okay to have an x times a y in a polynomial. Most of our polynomials we're going to look at are going to be looking a lot like this. Okay? Believe it or not, 12 is a polynomial. Just the number 12. The word polynomial means many, poly for many, nomial for number, so many numbers, right? Which is not very helpful description of it. These are not polynomials. So let me talk about some things that aren't allowed. The square root symbol is not, once you put that in, it's not a polynomial. These fractional exponents, which some of you may not know what those really mean yet. So we will learn about those later if you have not already seen them. But they're not polynomial. Negative exponents make it not a polynomial. This here, when the exponent is a variable, it's not a polynomial. And then this here, when the x's are in the denominator. So it's okay to have a fraction, but not okay to have the x in the bottom. When I say okay, I mean it's okay, it's just not a polynomial. And then here, the y is in the bottom. So we want to be able to recognize a polynomial because we're going to be studying techniques in this unit about how to solve them. And I don't want you to apply those tools to the wrong thing, right? Be like using a flathead screwdriver when you need a Phillips head screwdriver. Get what I'm saying? So yeah, we want to make sure that we're able to identify them. In this unit, it's not so hard because everything's pretty much going to be a polynomial. But when we come back together at the end of the course and we mix everything together, we want to make sure that we're able to identify and provide the proper tool. Okay, so let's talk about a polynomial. So this is kind of a working definition for us. It's an algebraic expression composed of terms with x to a non-negative power. I should really add a non-negative power, non-negative integer. Or I could just say whole number power, okay? By definition, a polynomial cannot be zero. So a polynomial can be a single constant, but that constant can't be zero. All right, polynomials can be described by their degree and the number of terms in the expression. And we'll use slightly different techniques depending on the degree and the number of terms. A monomial, mono meaning one, or nomial, monomial, I think that's how I spell it. It means one number, okay? It's a polynomial with one term. So it could have multiple numbers. It could be like 3x squared, but that's one term. Terms are separated by pluses and minuses. The number of terms in a polynomial is just equal to the number of monomials, which is, I think, an overly complicated way of describing that it's the number of chunks, okay? So terms are separated by pluses and minuses. So we can go and look at these example ones I gave you and see that this has 3 terms, 2, 3, 4 terms, 2 terms, 1 term. The degree of a monomial is the sum of the exponents of the variables in the monomial. That is a really complicated definition for a very simple idea, but there's a slight special case that we have to include in this definition. So the degree of a monomial, or in other words, the degree of a term, is simply the exponent. So this is a degree of 2, a degree of 1, and this would be a degree of 0. We could think of that as x to the 0 power. Anything to the 0 power is 1. So anytime you see a constant, that's x to the 0, because it's just that number times 1. Okay? That's a degree of 1, degree of 0, degree of 2, degree of 2. But here's the special case. We will not deal in this unit very often with having x and y's multiplied together. They'll come up mainly more in like unit 11, 12 kind of thing. And then not that much, more in pre-cal and calculus. But technically, you have to add the exponent on x. If there's no exponent on x, it's a 1. Okay? The exponent on y is a 1. So technically, you would add these together and get 2. You know, that may never come up again in the rest of the classroom, but I hate lying to you. So yeah, degree, technically you have to add them. Okay. The degree of a polynomial is equal to the degree of the highest degree monomial. So in other words, we can talk about the degree of a term, and it's important to understand that. I'm going to say stuff like, do this to the third degree term. Do that to the second degree term. But if I say this is a polynomial of degree 4, what I'm saying is the highest exponent overall was 4. So we could look here and we could say this polynomial has a degree of 2. This is a first degree, second degree, fifth degree, 0 degree, third degree. Okay? And we'll do slightly different techniques sometimes depending on the degree. And that's just what we've been saying. And proper classification of polynomials by degree and terms is absolutely essential, because we'll use different techniques depending on the degree and the term. So for this example, we're going to state the degree of each of the following monomials. We've already looked at a few of the examples. This is a 7th degree. This is a 0 degree. And you might be confused later, so you may want to say degree is equal to or something like that. It's your notes. Do what you want to do. This is a first degree. Maybe we could write it like that. And like I said, we're not going to see this too often, but technically this is a 5th degree, because you have to add the 2 and the 3 together.
Wait, it's 5 plus what?
5th degree. That's a TH. No worries. This here is a 5th degree as well. And then I included this kind of stupid example here. That's still just degree 2. I don't want to add the 3 and the 2 because that's just part of the constant. That's just saying that number is actually 125. It's the degree is affected by the exponents on the variable. Okay? Polynomials of degree 0 are called constant. It sure would be nice if mathematicians just stuck with one way of calling something and then didn't confuse everybody, but that's not what we're going to do. Degree 1 are called linear. We studied the linear unit a long time ago in this class. And they were polynomials, and they were all of degree 1. We've just finished 3 units, because it's one of the most biggest concepts in Algebra 2, that were all about quadratic expressions, equations, and functions. Degree 2 polynomials are called quadratic. Degree 3 are called cubic. Degree 4 are called quartic, like a quarter. And degree 5 are called quintic. So the only degree term that doesn't make any sense to me is quadratic, because I hear quadratic, I think 4, but it comes from the idea that the quadratic function makes a rectangle when you multiply it, if you've seen geometric representation. So that's kind of where that word comes from. All right, for higher degree polynomials, we'll simply say 6th degree, 7th degree, things like that. I don't have special names for them. And in fact, above degree 3, I would rather just call it 4th degree, 5th degree. But you will occasionally hear the words quartic and quintic. Okay, so let's state the degree of the following polynomials. This is a quadratic polynomial. It is quadratic because it is degree 2 as the highest degree. This is also quadratic. Because this is 1 plus 1. You add them together. So that's a really different thing. It's not like the quadratics we've seen. It turns out it's not a function. It makes a very interesting kind of shape, like ovals, or what we call ellipses, and hyperbolas, and things like that. This one would be a hyperbola, actually. This one here is what we call constant. It's constant. If you graph it, it's a horizontal line. It doesn't move. This is cubic. And this is quintic, because the highest degree term is 5. Polynomials also have special names based on their number of terms. We have monomials, we've already discussed. 2 terms are called a binomial. Bi, like a bicycle, meaning 2. This is also how the mathematician just goes on a diet. They binomial. Yep. All right. 3 terms are called a trinomial, like a tricycle has 3 wheels. Trinomial. For larger term polynomials, we'll stop trying to come up with fancy words, and we'll just say 4-term, 5-term, etc. All right, let's determine the number of terms in each polynomial. This has 2 terms, so it is a binomial. Specifically, we could call that a linear binomial. This is a quadratic binomial. This is a quintic trinomial. And this is a monomial. Even though it's got a 3 and an x to the 4th, it's just 1 term. Remember, terms are separated by pluses and minuses. All right. All right, I want you to classify each one of these polynomials based on the degrees and the terms. When possible, use the words that we've discussed for the degree. That's constant, linear, quadratic, cubic, quintic, quartic, and use the number of terms, monomial, binomial, trinomial, and then 4-term, 5-term, things like that. So give it a shot. Okay, so this is what you should have said. You should have said that this was a quadratic binomial. Maybe you said binomial quadratic, and that's fine. Just traditionally, it goes in that order, but that's not what's really important. What's important is that you know what those words mean to you. This here is a 4-term cubic or cubic 4-term polynomial. And I want to just take a brief second to just, kind of put a star by that. This is going to be a big emphasis in this unit, is how to solve an equation like that. So look forward to that. And you'll be something that you'll be able to do, but you probably can't do right now. The highest degree is 3, and that's what cubic means. Cubic means third. No, because they have to be multiplied together. You don't add 3 and 2 together and say it's 5th degree, because they would have to be like... And in order for that to happen, they actually have to be like 2 different letters. And I hate bringing that up. I've actually seen it. We don't give the Algebra 2 in the course exam, but I have, back in the day when they did, they actually would test that vocabulary or not. So I include it. It's not going to be a big deal in my class. For the most part, your degree is going to be the highest little number. 99 times out of 100, right? Okay. This is linear, and it's a monomial. And so, we already know these two things, we know what shape those makes. That would make a parabola. This would make a line. This is a constant monomial. It also makes a line, just like a linear, but the difference is it's a horizontal line. It's flat, has no change over time, doesn't go up or down. This is a sixth degree trinomial. And we will actually look at solving a few special cases of those. Anything beyond degree 3 becomes special cases to solve. There actually is a cubic formula that's used in math. We won't do it because it takes a whole lot of paper. But it's an interesting formula because it involves imaginary numbers in the middle of the problem, and then they go away and become real numbers. Even when you're only solving for real numbers, you have to use imaginary numbers. So it's kind of interesting. We won't do that, though, but that is an important formula. Usually done by computer nowadays. Example 1.4. Okay, we're going to simplify some expressions. This will be a little bit of review. You've probably done stuff like this in this class and in an earlier algebra class. We'll look at, there'll be a couple of things that might be new. All right, so in this one here, to simplify this, my goal is to get it in no grouping symbols, no parentheses, okay? So here, I just FOIL. X times x times a negative 2, 1 times x, and negative 2. And then I just bring that plus 3x down. I'm going to combine like terms. Oh, I didn't do it right, though. Negative 2 plus 1 plus 3. That'd be negative 2 plus 4. This is a plus 2. And then a minus 2. When possible, we prefer to have it in decreasing degree. That's standard form. That makes some of the processes that we'll be doing easier. All right, let's do this one. We've seen stuff like this before. I call this super foiling. You have to take it to, you have to multiply it to each one of these twice. So x times x is x cubed. And then x times a negative 3x is a negative 3x squared. And then x times 1 is a plus x. Then we do the 2 plus 2x squared minus 6x plus 2. All right, so this is x cubed minus x squared minus 5x plus 2. All right, on this next one, it's going to really help if we know how to square a binomial. Don't call this x squared plus 1 or something like that. You have to square the binomial. It's a squared, so x squared. Multiply these two together and double it, so minus 2x, and then square that plus 1. Then combine like terms. All right, on this one here, I'm going to distribute the x. So 5x minus x squared. And then you really want to be careful with minus signs out in front of things that are squared. I cannot distribute this negative because the exponent comes before multiplication. That would be violating the order of operations. But I need to be really careful. So what I do is I put a square bracket there just to kind of, I don't know why I like to do square brackets here. I just do, but they're the same as a parenthesis. Now I'm going to square this binomial. So that's square the first time, multiply the two together and double it, square the last term, like that. Then I'll distribute the negative after I've squared it. And that gives me a negative 2x squared minus x minus 4 if I put it in order. Okay, now we have x plus 4 cubed. So to do that, I need to do x plus 4 times x plus 4 times x plus 4. This, you're telling me this should be a positive x, and you are correct. Thank you very much. Yes, that should be a plus x. Minus 5 to Wilshire. All right, let's multiply that together. That's just squaring it, right? We know what that becomes. It becomes x squared plus 8x plus 16. But then I got to put in parentheses because I still got to do another x plus 4. So x times x squared is x cubed. Then plus 8x squared plus 16x. Now I got to do the 4. Plus 4x squared plus 32x. And 16 times 4 is plus 64. Because that's 4 cubed. Combine like terms. And I don't know about you, but that's a lot of work. But one important thing to point out is what this is not. This is not x cubed plus 4 cubed. No way. It became this big, long thing. And if you bear with me, I'll try and make that a little easier coming up in a couple pages. All right, now let's kind of apply that again. This is our difference of 2 square pattern. It becomes x squared minus 1. But then I've got to keep this negative while I take care of this whole thing. And in a situation like this, I would actually recommend scratch paper and doing what we just did with that thing and then putting the answer there. Okay? So that's exactly what I'm going to do. I'm going to take the back of this previous page and I'm just going to say, okay, I need to figure out what x plus 2 cubed is. I don't want to spend a whole bunch of paper doing that and getting a chance of messing up. Okay? So let's just do it off to the side. Or you can just write down the answer in your notes because we're going to learn how to do this in a different way in a minute. All right. So this is x plus 2 squared times x plus 2. We know what x plus 2 squared is. That's x squared plus 4x plus 4 times x plus 2. Then we'll distribute. I get x cubed plus 4x squared plus 4x. Then I get plus 2x squared plus 8x plus 8, which gives me x cubed plus 6x squared plus 12x and plus 8. That's what I'm going to put right there. All right. And I get a negative x cubed minus 6x squared minus 12x minus 8. And I get negative x cubed minus 5x squared. Let's see, minus 12x and then minus 9. I think I did that right. There, that one. And then those two make negative 5. I only had that one. Okay. All right, so I've got some for you to practice doing. So go ahead and do that. Okay, so on this one here, we want to just, it's basically just foiling. So x cubed plus 3x, then minus 5x squared, then minus 15, and we'll just kind of put everything together. Or actually, there aren't any like terms, but I will rewrite it. I prefer to rewrite it like that. It makes solving it easier. If you didn't, that's okay. Later on, you'll just want to. All right, multiply here. X cubed plus 3x squared minus 5x. Then minus 2x squared minus 6x and plus 10. And we should have a couple of things that we can combine here. So x cubed, 3 minus 2 is 1x squared, negative 11x plus 10. Just quick thing to point out, in A and B, we multiplied together a linear and a quadratic on each case and ended up with a cubic. In other words, degree 1 and degree 2 makes degree 3. Because 1 plus 2 is 3 and 1 plus 2 is 3. All right, the x minus 3 cubed. X minus 3 squared is x squared minus 6x plus 9. So once you do that, then you just have to multiply that times x minus 3. So I can go this way to this way or this way to that way. I prefer to distribute the small thing to the big thing, though. So x cubed minus 6x squared plus 9x minus 3x squared plus 18x minus 27. So x cubed minus 9x squared plus 27x minus 27. All right, on the next one, we need to square this binomial. So it's 4x squared minus 4x plus 1, and then multiply it again. So you remember, this is 2x minus 1 squared times 2x minus 1. That's what makes it 2x minus 1 cubed. Now I'll distribute and get 8x cubed minus 8x squared plus 2x. Then negative 4x squared plus 4x minus 1. So 8x cubed minus 12x squared plus 6x minus 1. All right, we're now on to letter E. I have x plus 5 squared. That's x squared plus 10x plus 25. And I'll distribute the minus 3x minus 3 and combine like terms. Oh, I messed up. X squared plus 7x plus 22. Okay, let's do x plus 2 squared. That's x squared plus 4x plus 4. And then what I would do is you could actually distribute the minus to the x plus 3, and then you'd have negative x minus 3, which you'd have to FOIL. I'd rather distribute after I FOIL, so I'm just going to put that in brackets here and multiply this way, giving myself x squared. That'll be a plus x minus 6. And then I'll distribute, and we're actually going to lose our quadratic term, giving us 3x plus 10, so we ended up going back down to a linear. All right, the next practice problem, you might have been a little surprised what that's doing here. So I want you to describe the pattern demonstrated in the numbers. Some people look at this and they say, I don't see a pattern at all. Maybe you notice the ones on the start of each row. Other people see it really quickly. Well, there's going to be one here and here for sure. Now, then, to fill in the next two rows, take a look at the 2. It starts with a 1, and then 2 is 1 plus 1. The 3 is 1 plus 2 is 3, 2 plus 1 is 3. This 4 is 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. So yeah, 1 plus 5 is 6, 5 plus 10 is 15, 10 plus 10 is 20, 10 plus 5 is 15, 5 plus 1 is 6. Fill in the next row for me. Okay, so now let's figure out this last row. It should be 1, 7, 21, 35, 35, 21, 7, and 1. Nice. The triangular arrangements of numbers so that each value is the sum of the values directly above it is called Pascal's triangle. Pascal's triangle. That's right. After the famous mathematician and philosopher Blaise Pascal. You may be familiar with Blaise Pascal's other famous thing. He has a few famous things, but his most famous thing is, as a philosopher, he wrote in Latin, cognito ergo sum, which is Latin for I think, therefore I am. which is a very interesting piece of philosophy. People quote that all the time as if it's some sort of like demand to think and therefore you'll be. It's not at all what he meant by that. He is actually describing, he was an existentialist. He was fascinated with what it meant to be alive and how we should behave because of that. And so he was a mathematician and a philosopher. So he took his mathematical training and applied it to philosophy of the world. And we know that in mathematics we set down postulates that are not proven but taken as given, right? And we want to then prove things logically step by step. So his postulate in this famous philosophical treatise is he wants to make sure that we all agree that we exist, which is actually a question people have. Perhaps you're familiar with the allegory of the cave, things like that. Do I really exist in a world? And what he said was, well, I think, therefore I must exist, and then went built on from there. Now, if you can't tell, I am a huge Blaise Pascal fan. When my wife was pregnant with our first child, which I was woefully not ready for mentally, but we waited to find out if the baby would be a boy or a girl, and of course we had names for each one of our children, depending on what gender they would be born, and I fought vehemently that if my firstborn was a boy, that we would name him Pascal. And that did not go over well with my wife. I said, I'll compromise. I said, Blaise. Blaise. That's a good name, right? Not having it. Not having it. I lost that battle. Turned out my firstborn was a girl anyway. But I then, several years later, I was at calculus camp. And yes, teachers go to calculus camp. It was fun. And I met someone, and they introduced his family, as he's a calculus teacher, and he introduced me. His eldest son had a middle name of Pascal. And I said, you did it. He goes, I knew I could. And he told me, I said, I tried that because I knew it would be too much to ask for the first name. So I went for the middle name. That's brilliant. Brilliant. Um, but yeah, no, he is super awesome. And this is his triangle. He didn't make the triangle, y'all. He's famous for connecting this triangle to what we're doing right now. But he didn't do that first either. But he made it famous. You know, I mean, in mathematics, so many things are named after people that just made it popular. You know, he got it trending, if you will. But I don't mean to imply that he's the first person. We've actually seen this triangle in Chinese mathematics, I think even in Egypt. So it's all over the place. Anyway. So we're going to use a calculator, which you probably don't have since I never issued them this year because, well, you know why. But we're going to do this together. This is we could do this with a website though. But there's plenty of websites you can go to that will expand it by number. We'll just use this calculator. So here we go. We're going to say alpha A plus alpha b, and I'm going to raise it to the 0 power. And on this calculator, you have to say expand. So I'd say algebra 2, that's F2, expand. And there we go. The answer is 1. That was anticlimactic, but anything to the 0 power is 1. That should not surprise us. Now we're going to put to the first power, and I get a plus b. So 1a plus 1b, right? Now, I'm not a big person about putting implied ones. They're not necessary, but just for fun, let's put them this time. Now we're going to put the 2. And that is a squared plus 2ab plus b squared. I hope you know that pattern. We have talked about it a lot. So it's 1a squared plus 2ab plus 1b squared. All right, let's do the third power. All right, you'll see that my calculator did it for me, right? I'll just write it down for us. We got 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. Huh. Let's do the fourth. All right, so I multiplied it out on a fourth. Let's see what the a plus b to the fourth is. Well, I got 1a to the fourth plus 4a to the third b plus 6a to the second b to the second plus 4ab cubed plus 1b to the fourth. Now, if you would just look up at the top of the page, you might see where those numbers are from. They're from Pascal's triangle. That's right. Now, back in Pascal's day, they did not have the ability to multiply a plus b to the fourth with a calculator. So this connection between a triangle and this was very advantageous. Yes? And this has got applications beyond just polynomials. It actually has to do with probability as well, and I would love to dive into that with you. But I don't have time. That's a 4. 1, 4, 6, 4, 1. So now that we've seen the pattern, can we figure out, we'll do the practice problem together, can we figure out what a plus b to the fifth must be? So look carefully at the constants, the coefficients. They come from the triangle. So let's just start with that. 1 plus 5 plus 10 plus 10 plus 5 plus 1. Do we all agree that those will be the numbers that will be there? They have to. Notice that the exponent tells you the row to look at. Okay? And typically in Pascal's triangle, we call this row 0, row 1, row 2, row 3. The row number actually comes from the second number. Okay? All right, now, the powers on A will start at 5. And then we'll go down to 4. Then it goes down to 3, then 2, then 1, and then 0. But a to the 0 is just 1. Do you see that in the pattern for a plus b to the fourth? It was a to the 4, 3, 2, 1, 0. And I'm just going to do the exact same thing with the b's, but starting on the other end. So b to the fifth, b to the fourth, b to the third, b to the second, b to the first, b to the 0. So you can just start on the left and then start on the right, or you can realize that one goes down as the other comes up. And it doesn't matter which one because it's symmetric. So I want you to realize that if we were to multiply a plus b to the fifth by hand, we just did a plus b to the fifth pretty quickly. If we were to do that by hand, that would be a paper worth of work. That would be a lot of work, right? Okay, let's expand each of the following polynomials using Pascal's triangle as an aid. The one that I really want you to know, we already know the 1, 2, 1 pattern. We've been using that almost all year. But now I want you to know that 1, 3, 3, 1. Really get that one down. That's going to help you a lot. Beyond that, you may not come across it that often. And you can always draw out your triangle. But all right, so here's the deal. It's going to be 1 plus 3 plus 3 plus 1. Because it's x plus 1 cubed. So we're looking right here. Okay, now we're going to start with this. This is my A, and that's my B. Okay, so we're going to start with the x, and we're going to say x to the third, x to the second, x to the first, x to the 0 I don't write, because that's just times 1. Now we do the 1 times 1 to the first, or to the third, 1 to the second, 1 to the first, 1 to the 0. But 1 to any power is just 1, so in fact we're done right now. So what I do now is I rewrite it, I simplify, I combine anything I need to combine, and get rid of the unnecessary ones. So I do this in a couple of steps, and I want you to as well. Okay? Don't try and do it all in one step. It's not that easy. All right, let's try the next one. Fourth power. 1 plus 4. Give yourself plenty of room, okay? Plus 6 plus 4 plus 1. Okay, now we have 2x. that needs to start at the fourth power and go down. So we can go through and write it like that, like that, but we're just going to have to apply the exponent to each one of them. Okay? So 2 to the fourth is 16, and then x to the fourth. Now we do the third power. 2 to the third is 8. Notice I'm timesing. 8x to the third. 2 to the second is 4, so it's times 4x to the second. 2x to the first is just times 2x. And then 2x to the 0 is just a 1. All right, now we got to do the negative 1. So over here, we start on the right. We do negative 1 to the fourth. Negative 1 to the fourth is a positive 1. Then I do negative 1 to the first. That's a negative 1 because it's an odd exponent. Then I do negative 1 to the second. That's a positive 1. Then I do negative 1 to the third. That's a negative 1. Oh, I'm sorry. I did it in the wrong. I said it backwards. This was to the fourth, which is positive, to the third, which is odd, to the second, which is even, to the first, which is an odd number, so it's negative, and then to 0. But basically, they just alternate signs. All right, then we'll simplify. 16x to the fourth minus 32x to the third plus 24x to the second minus 8x plus 1. All right, that one's a pretty tough one, I think. Anytime you have a negative, you have to deal with, and then the 2. So that one was tough, but it's okay. All right, now we're going to do x plus 2 to the fourth. This will be a nice example to end with because it's a little bit more straightforward by the pattern. All right, fourth power we know is 1 plus 4 plus 4. Ooh, that's not true. Plus 6 plus 4 plus 1. And you can always generate that triangle if you need to. Just start with 1, 1, 1, 1, 2, 1, and go from there. All right, so the powers on x start at 4 and count down. All right. And then you can either start with 2 to the 0 here and count up, or you can start with 2 to the fourth over here and go left. I'll start over here with 2 to the fourth. So now I got to do the 2. 2 to the fourth is 16. 2 times 2 is 4. That's squared. Times 2 is 8. That's cubed. Times 2 is 16. Then times 2 to the third, which is 8. Then times 2 to the second, which is 4. Then times 2 to the first, which is 2. Then times 2 to the 0, which is 1. Though this is x to the fourth plus 8x cubed plus 24x squared plus 32x plus 16. Now, I know this seems tedious and probably not your favorite activity, but I hope you appreciate how much time it is actually saving us. This is something that is done a lot in calculus and other math classes. Expanding a binomial, very important. So we want to be familiar with it. You'll study it in much greater detail in pre-cal, though. All right, so I want you to do practice problem 1.5. And then there is an exit ticket that you can check out. See if you can work through that, and that'll be it.